hold on. Greetings in the love and light of the Infinite Creator. I'm Andrii, and joined today by Roger, Bentley, Jean Laherrere, Stan Osserman, and Dan Gowin. And we will be diving into the $1 million oil datasets, as well as, if Simon Michaux joins us, we'll be doing the Hawaii report. And then Dan and Stan have some oil updates for us. All right, Roger, did you want to introduce yourself and Jean at first?
Yes.
Yeah.
Okay. Thank you, folks. So, yes, I was asked. Hello, it's all gone. Oh, here we go. Yes, I was asked to. I'll do a quick introduction, and then we go to slides. I was asked to present something about $1 million data sets. Jean and I and other people have been extraordinarily privileged, if it is the right word, privileged to use these oil industry data. And the only pain is that then nobody else believes what we say. So that is a bit grim, but slowly, more data comes out. We point people to where they can get the data and so on. Okay, so there's slide one. You put it right? Excellent, thank you, Andrii. Brilliant. So it was. I don't know who christened it $1 million data sets, but anyway, the word came from somewhere. Probably I used it loosely. So I was asked by Colin Campbell years ago to start a journal called The Oil Age. It's up on the web there. He's got some wonderful articles people kindly contributed, though it came to an end. We didn't have enough takers. I used to work in cybernetics, and then I was for a year a coordinator of the Oil Depletion Analysis Centre in London. And Jean Laherrere, who knows 4 million times more than I do about all this, is a co-author, and as you can see, was head senior man at Total, and had access to the data until fairly recently. It's been a little harder for him to get more recently. Jean, that's correct, isn't it? Less access to the data.
Yes.
Yeah. Okay, let's go to slide 2, please. There we go. So first of all, a caveat. The full data sets I'm going to discuss do indeed have an annual license fee. It's only a license fee annually of $1 million a year, and the oil majors certainly were buying them. I'm pretty sure still are, but I haven't talked to anybody recently enough to be certain. And that includes a lot of analysis and other stuff when they buy the whole package from the companies. I'll explain a little later. But if you just want what we're talking about here and tells you about future oil production, you need the exploration and production data sets by project and by field, by individual oil field and by individual project, mainly for the non-conventionals. Then you only pay $100,000 a year. So you pay that much. You can't print it, you can't publish it, but you pay that much. But some of the companies, Rystad for one, and Consultants, I think, for another, IHS Energy, have offered these data sets for less money to academic institutions and similar institutions. And I'll explain later who some of those are. And the data set I actually used when I was at the Oil Depletion Centre in London back in about the year 2001 was still extraordinarily useful. It wasn't by field and it wasn't by project, but it was by country, and it still let you see what each country has actually discovered as opposed to the data I'll explain in a minute. And here is Jean with a wonderful book. Okay, next slide, please.
Here's John showing the book.
Yes, there we go. This is Jean with an amazing book from Petra Consultants with all the data undiscovered. 1995, Jean, was it 1995?
I think so. 1994,
okay. 1994. So next slide, please, if you don't mind. So there are two very, very different types of oil data sets. The difference between them is immense, and this difference has misled oil analysts for decades and decades, right back to the time of Hubbard, and still misleads many, many, many people today, I'm afraid. Dataset 1 is in the public domain. It's on proved oil reserves by country. So if you read the data on a country's proved oil reserves, this is the one you'll read. You see them in newspapers, magazines, on the television all the time. Published by the US Energy Information Administration, so a very high mark of respect, OPEC, Oil and Gas Journal, World Oil, data sets like Sister, Our World in Data, and formerly was in BP Statistical Review. Am I making too much noise, you guys? Something?
Oh, it says someone, hold on.
Got it.
Hold on. Someone.
I think we should all be mute except the talker.
Yes.
Really?
Yes. Ivor is supposed to be moderating. Hold on. I'm trying to mute. Here, I'm going to mute everybody, and then you unmute yourself. Okay, Roger.
I mute. Yeah, unless I.
Okay, unmute yourself, Roger. Do you know where the mute button is? It is at the bottom on the right. Here. Ask to unmute. Oh, Roger. So if you have to move around in the screen and then find the unmute button, it should be at the bottom. It looks like a little microphone with it crossed out. Gene, you as well. If you can unmute yourself. Sorry for the technical difficulties. Oh, there's World Oils.
Yeah.
Roger.
Now I'm alive. Yeah,
got it.
Good. Got it. Yeah. So back to the slides, if you don't mind.
Okay, great.
Brilliant. Can everybody hear me?
Yes.
Good. So 2 types of data set. The one you get in the public domain from these really respectable organizations, Oil and Gas Journal. I can talk a lot more, but I won't. Next slide, please.
Okay.
And the second data set, type of data set, oil industry data, proved plus probable, not proved, but proved plus probable oil reserves by field and by project, aggregated, backdated. And this comes from oil companies, some governments, but you've got to be careful which data sets you access, and the oil consultancies, including what was Petra Consultants. They set it up originally. IHS Energy, Wood Mackenzie, Global Shift.co.uk, and most recently Rystad. And these are what we call $100,000 data sets. You pay that per year. And if you want to know anything about oil or gas, only use these data. Never touch the proved reserves data. Okay, next slide, please. So what is the difference? Public domain proved oil reserves data generally proved are underestimated, because proved and probable is taken to be a kind of 50% likely. So proved are lower estimates, underestimated, but they've also become badly overestimated in some cases. OPEC and some others I'll show you in a minute. And amazingly, annual changes are often not reported annually, and sometimes some countries don't change their proved reserves data for decades and decades.
Wow.
Dataset 2, the type of dataset, come from oil industry sources. I just mentioned the consultancies. They are proved plus probable. They're fairly reliable, although Jean Laherrere, good analysis that he is, has found errors and problems, and quite correctly. So even here, you've got to be careful. Okay, next slide, please. We won't take too long. Right, let's examine the difference. Here's some numbers. In red, in the line 1p in red, are the public domain proved reserves. These come from BP stats of a couple of years ago, but they're all basically the same from everybody. Where, for instance, you can see that, let's say, Iraq had proved reserves of 145, this is billion barrels, 145 billion barrels, and the world had a wonderful 1,732 billion barrels of proved reserves oil, a lovely solid number. However, if you look at Rystad, oh boy, for Iraq, instead of 145, it's 31. Now, this is not just, marginal errors. This is magic errors, differences. And for the world, 450 instead of 1,732. So the multiplier multiplies what you have to multiply the oil industry data by for reserves, proved reserves now, be fair, proved reserves, to get to the public domain data. And a lovely multiplier there is Venezuela, thank you, Andrii, times 60. So Rystad thinks that Venezuela has 5 gigabarrels of proved reserves, 5. And if you go online and any time you read any newspaper report at all, they will tell you that Venezuela's got the largest oil reserves in the world at 304. Now, of course, there is some basis behind all of this, but that we could discuss in another presentation. But the crucial thing are these huge differences. Now, Rystad does do proved plus probable, the 50% likely ones, and that's the line under the blue multiplier. And there for Venezuela, for instance, you can see they've got 9 gigabarrels. So they think the proved and probable for Venezuela is not 300, but 9. And for the world, 738. So less than half of the proved reserves are in proved plus probable. They do contingent. If there was a lot more oil they think might be found in these places, not might be found, might be producible in reserves. And finally, 2PCX is proved plus probable plus contingent plus exploration. If you go and look for more, you'll find some more. So Rystad thinks the total of proved plus probable plus exploring is probably 1,500 billion barrels, whereas the 1P, the secure number that's supposed to be we all rely on, is bigger still. And so the multiplier there is the multiplier of 2PCX from Rystad to get up to the single 1P. So you're comparing proved oil reserves with proved and probable and contingent and exploration. There can be no other professional area in the world where the data are so disparate. What's in the public domain, quoted in all the television, newspaper, journal, oil and gas journal, world oil. Only today, Jean sent me a paper by a man from Texas Railroad Commission. And of course, he's quoting proved oil reserves without turning a hair. If this wasn't true, you would think I was making it up. And you can just go and check all these numbers. Rystad data in a press release July last year. And the proved oil reserves are all over the shop. You can find them anyway.
So I have a question. So is the Rystad data closer to what's in the $100,000 and $1 million data sets?
They are. They are Rystad is one of the. I went a bit quickly, but they are one of the $100,000 data sets. There's the $100,000 of those 5. Is it 5 consultancies? IHS Energy, Wood Mackenzie, Rystad, Global Shift, and whatever 4 is it 4 or 5? Anyway, whatever it is, those are the $100,000 data sets. All of them. Global Shift is a bit cheaper. They're different. Dr. Michael Smith, for a reason I could go into. But the other 3, IHS, Wood Mackenzie, Rystad, 3 are all $100,000 a year to get the data sets. So, and they're all rather similar. We've looked at them. Jean and I have compared them and looked at them. Hello, Charlie. Nice to see your face in the thingy. So yes, so we've all, Jean and I have compared them. We've had access to. I've had access to all of them except Wood Mackenzie. Good old Wood Mackenzie never shares information with academics. All the others do. I've had the whole data sets from Global Shift. I've seen Uppsala's whole data set. I've seen a lot of Rystad's data set.
Okay. I think Jean wanted to say something, but you have to unmute, Jean. You're still muted. You have to click on the button at the bottom. So if you move, and then there's a little microphone.
In your little picture, Jean.
Yes.
You have to look at your little picture and then click away.
Find the little microphone at the bottom. Oh, he disappeared.
Oh.
Okay. Well, he might return.
I'm sure he will. I'm sure he will. Okay, we're nearly done, aren't we? So when Jean comes back, he's the co-author of all this, of course. Right. Mm-hmm. So there we go. That's so everything from Rystad is the $100,000. So what this whole talk is called the $1 Million, and I'm sure you can pay them a lot more, but this is just from their oil and gas by project, by field data sets. And those are their numbers, and they're very similar to everybody else's. Nobody's in the $100,000 data set for obvious reasons. They all come from the oil companies, and they all know what's been discovered in the fields. You can argue a bit, and the definitions for 1P, 2P, as Jean will tell you, are all standard. He worked on them for many years in the industry. They're all standardized. So they're all numbers, are all very similar. So I give Rystad because they're the only one who publishes them regularly, but everybody else has similar data. Next slide, please, Trey.
You need to clarify which data set is which.
Of which? Table. Of the previous slides?
Yeah,
Charlie?
The previous table.
Yes. Okay, back to there. I know it's quite complicated, so let's go. Let's look
it
at
isn't that complicated, but clarify. They're different.
Yes, very clear. Okay, the red line is the public domain red data. It actually came from BP Stats, but you'll find the similar data, not identical, from other people. OPEC is a bit different generally. BP Stats.
Maybe put the source all the way to the right.
Charlie, say it again.
Maybe put the source all the way to the right. Extra column.
Sorry, what? The source.
The source.
But there's only two sources, Charlie. There's only public domain and
Rystad. Over here.
There's only public domain and Rystad.
It's red versus black?
Yeah, red versus black. Yeah, very good. Black is Rystad, red is public domain.
All right. Okay. So are we ready to go to the next slide?
Yes, please, Andrii. Yes, please.
Okay. Oh, and we have Jean.
Jean, come back, please.
Oh, he's still muted. Jean, you'll have to find the microphone button and then unmute it.
Bottom left.
There. Okay. You did it.
Good.
Okay, now you could do the same with your video, and then we'll be able to see you.
Video. Okay, start video.
Yes.
Okay.
There.
Sorry.
Okay, good.
Your name.
Right.
Sorry, I'm completely mad.
It's okay. Okay, you did it.
I did.
Okay,
I did it. But you know, I don't know who is wrong, my computer or myself, but I think it is both.
So what did you want?
I was 94 last week.
Oh wow! Congratulations! Happy birthday!
You can explain. So,
How old?
94.
I was born in 1931.
Mm-hmm. So you said you wanted to share something?
Yes,
Yes, go
you have to add that under the SEC, Security Exchange Commission, all the oil companies listed on the U.S. market are obliged to use the SEC proven reserve, which is completely wrong. So it is if the company are reporting the 1P, it is because they are obliged by the SEC. You see, in the past, for example, Total or Exxon was reporting 2P, but no, they don't anymore because it is forbidden by the SEC.
John, that's a very good point to make. I didn't make that. So for individual companies, they're employed by the Securities Exchange Commission. And of course, the countries can just report what they like. And most of those big differences for the OPEC countries were they jumped up their reserves in the 80s when they were all competing for quotas, and your amount you could pump legally under your quotas was related to your reserves. So you pushed up your reserves, and most of them have never pushed them down again. So there we go. Okay, thank you, Jean. Very good point. Next slide, that one. So let's have a look at this is oil industry data. This is IHS Energy. These data are very difficult to get, but they did it through a report for the United Kingdom Energy Research Centre, published by Sorrell and Miller. And this is a lovely plot. The top line, the black line at the top with the squares, isn't it, is discovery, the global cumulative discovery of ever since 1900 up to 2011. I think that's when the data was stopped, 2011. And then the triangles are how much oil we've used. This is cumulative. So that was what we discovered. That's cumulative use. And therefore, the difference between is reserves. And you can see by about 1980, reserves peaked and went down because our consumption had been roaring up. And you can now, I can't show you the data because I'm not allowed to, but you can extrapolate a bit further when you have the data. But this came into the public domain and was a real landmark that we could show these data. Okay, next slide, please. This is from Jean. I think Patrick Bockrans or somebody's got another good graphs like this, which I need to use, but in red are more important than the big errors we showed on the previous slide, Charlie, with those numbers and the errors. More important is the rate of change over time. And the red line is proved reserves, and this is over time from 1920 till 2020 or something. They've been going up and up and up, not linearly, but in kind of big steps, up and up and up and up towards that 1762 we saw before. Whereas the oil industry data, not the ones they published for the SEC, but their own data that comes from the consultancies, did indeed peak at about 1980, have been falling ever since. And this wonderful chart is from Jean, and Jean is quite brave about what he publishes. Because there are, with some of the researchers, Colin Campbell and others, have been threatened by the data companies saying don't publish our data. So you have to be a little bit flexible. I used to give the data in conferences like this or meetings like this, but not publish them in papers. Anyway, so proved reserves up and up and up, and you get people like Art Berman. I don't think he's in this meeting now, but Art Berman loves to quote, "Oh, the reserves have gone up and up and up." Can keep going up, proved reserves, absolute tosh, they've gone over and gone down. Next slide, please. Andrii, you're doing a good job. So who has access? I'm not going to go through all this, but these are all the people who have had access to the oil industry 2+ proved plus probable data. I won't go through them, but you've got some of the names. You can read it later. Next slide, please. To access the data, we said they're very difficult to get. You can either have $100,000 in your pockets, that's okay, but you can't publish them, or else the Reichstag press releases help. And then Jean Laherrere does sterling work, and you can go to this other company, Global Shift, who are a consultancy. They do exist, but they're much more open to releasing data, and these are their data. Wonderfully showing how since 2005, global conventional oil has been on resource limited plateau. And so ever since 2005, we've had to use the more expensive non-conventional oils. Most analysts haven't got a clue about this, but 2005 is when we stopped using conventional, increasing conventional, not stopped using it, stopped increasing, and have gone up with the non-conventionals, which shown there are mostly NGLs. Some, of course, is US light tight, and some is Canadian tar sands and Venezuelan. So, and then there's a little bit of biofuels at the top, that little green slithery of biofuels. But 2005 was a landmark when the world reached its plateau, essentially resource limited plateau of conventional oil. Staggering, still not known in most analysts' minds, but it's all there in the data. Next slide, please. Further reading, if you've got time, this wonderful stuff. If you only read one thing, read Campbell and Laherrere's End of Cheap Oil. It explains all this. It gives the good data. It shows how you do your sums. It shows how you forecast it. Just a brilliant paper. Next slide.
I am presently writing with Hugo the term revisiting my 1998
That's
paper.
right. Jean is with Hugo Duterte are revisiting it, looking at some of the assumptions and being a good scientist and going back and questioning it. Last slide. Next slide, please. Further reading 2. Keep going. Next slide, please. Conclusions. Here we go. Using the misleading public domain, proved oil reserves were published by all those famous organizations, IEA, OPEC, oil and gas. Don't worry about oil supply. Reserves are always increasing. And Art Berman said this the other day. Just tosh. Instead, you've got to use the $100,000 oil industry data, as Jean, as Colin, as I, and plenty of Michael Smith and Miller do. And we're going to try. I've been trying to get my energy institute in Energy Institute in London, of which I'm a member, unsuccessfully so far. But I've been telling them they really need to hold an invite-only workshop. Bring in the proved people, bring in the oil industry people round a table or online, and hammer all this out. It's just atrocious that the world's largest single energy source is so badly documented. Thank you, everybody, for listening, and Jean for being co-author.
Well, I want to add two things. There is only one country which is publishing field data. It is UK. So UK provide all the data by field. You have also the US for the Gulf of Mexico.
Yes.
With BOEM. And you have also Norway, but Roger, you forget to add that you have several reserve classification. You have the SPA, you have the SEC, you have the Norway, which is completely different reserve, which is they call established reserve. So I don't know exactly what the correlation with 2P. And you have the Russian. And you see the Russian classification was by Kalimov in 1979. And he said it's the best classification. But in 1993, the same Kalimov says that their classification was grossly exaggerated. So he said it's bullshit. And most of what it is reported by IHS or Petro Consultant, or what they were calling 2P, was in fact for Russia. For Soviet Union was ABC1, which is more, because ABC1 is supposed to be 30 or 40% more than 2P.
John, very, very good point. So if anybody really wants to understand this, go and ask Jean. Jean knows it. I'm happy to gloss over it, but Jean is l'expert. Merci beaucoup à tous.
Okay. So now it's questions. Did anyone in the audience here have questions for either Jean or Roger? Ivor, go ahead.
So it sounds like everything that we've been saying all this time, we were right. Is that possible? I mean, it's almost like there's a big smoke screen over the last 20 years, especially with fracking and things like that. And they're trying to cover it all up. But in fact, 2005 was kind of the peak. And 2018 was kind of the peak of even all the nonsense that they came up with on top of it.
I'll reply to that briefly. First of all, I used to work for the oil companies, as did Jean, everybody. No, covering it up is not right. It's not right. It is, as Jean explained, the oil companies have to do individually have to do what SEC tells them to do. Other people have their own standards. OPEC countries, of course, were all fighting for quota back in the 80s, so they did what they had to do. No, I'm not a cover-up man. It's just the way it is, and this is how it's evolved. And if you look at Global Shift's forecasts, and it's all online, they do show conventional oil can go up a little bit for the next few years. So I say we're at plateau. We're essentially at plateau. If you really pushed, you could put it up a little bit, but essentially we've hit the plateau of resource-limited plateau of conventional. But cover up, no, it's just the way it is.
Well, you have to realize that in the same company, you have several people estimating reserve. So you have the geologist, you have the reserve engineer, you have the producer, and they are all different. So there is not one reserve in a company. There are several several reserves from several sources. So you have a range of reserve, not one.
Yes,
Okay, thank you.
quite.
Simon is next. Simon, you have to unmute.
Hello. Hello, Roger. Excellent work again, Sean. Excellent work. I'm currently, let me get rid of that hand for you. I'm currently, lower the hand. Yeah. I'm currently working on mineral intelligence of data patterns in the mining industry. And I've just recently mapped the whole Chinese enterprise. And I have picked up on a pattern where what they're getting us to look at and what they're actually controlling are two different things. We've been bamboozled into looking at the wrong thing. It's not that the information wasn't there. We've been convinced different things are important. What I found also is in the minerals industry, offtake agreements are important. Like, for example, we will actually quote what nation state does what mining. Like for example, in Belarus, what was mined? In Poland, what was mined? And of course, countries don't mine, companies do. Now, what I'm starting to pick up on, for example, rare earth mining in China is very high. But then the next country that is Myanmar in Burma. But the company that does the mining in Burma is a state-owned enterprise that is Chinese. So even though it's in Burma, it's actually Chinese. So also there's a sleight of hand in the data here. My question is this: are you seeing any sleight of hand strategies about the way the data is being presented that is leading analysts in the wrong direction?
I'll reply to that in my extent I know. It's a sensible, I follow the question, very sensible. I don't think there's quite the parallel because the data are just so hugely different in the public domain and the oil industry, or the oil industry company data. We have, of course, moved massively. It used to be all the oil was controlled by the Seven Sisters, and all that control has largely gone to the big oil companies, the Middle East companies, and so on, in Venezuela. They become nationalized. And so I except for the Middle East ones, the OPEC, who are quoting their numbers back from the 80s and not changing it, and people like Canada and Venezuela, who are understandably putting in large amounts of non-conventional. But this is where Rystad differs from the government, says, you're not allowed to report that under the sort of protocols that Jean carefully worked out with the other industry people all those years ago. No, it's a very good question, but I don't think it's a good question because China has moved into some of these oil producing. But no, I think we'll see something a bit different from what you see in minerals, Simon.
Okay.
Next question from Charlie. You have to unmute, Charlie. There.
I don't want to criticize your fine presentation. I just want to say that in looking at all this, you got to pay an awful lot of attention to what people are calling oil. And this, we started in our paper with a big section on definitions. And in the United States, for example, a third of our oil is natural gas liquids.
Yep.
And I think natural gas liquids are going to be more and more important going into the future because natural gas probably is peaking after oil. And so, I mean, it's amazing when I dug into the US statistics, how they seem to be hiding the importance of natural gas liquids in the official statistics.
Good point. I'll reply, Charlie. You always have good points. That plot I did from Global Shift, the one that next to last plot or whatever it was, showed how big the natural gas liquids are. There's a lot in America, as you say. There's quite a lot in Saudi Arabia and so on, quite large percentages. You're quite right. You have to split them all out. The paper Charlie's referring to is just an excellent paper, 2022, wasn't it? Charlie, you were the first author, wasn't it? No, Jean, first author, then Charlie, then me, and then so on. And it was called How Much Oil? What was it called, Charlie? How Much Oil There Really Is? What was it called?
Remains, I don't know. I can't remember.
how much oil remains separating fact from fiction. That's right.
Yeah,
and
that's it. Yeah.
And it's a bit of a difficult read because a lot of us contributed and we went forward and backwards, and then the journal wanted changes. But so it's a little bit more complex than I would like. But if you want an up-to-date, good, current summary of this whole caboodle, that paper by Jean as the primary author, then Charlie, then me, is an excellent paper in biophysical economics and sustainability.
All right, thank you. Okay, so if there's no other questions, I know Simon has a presentation for us.
Yes, thank you, everybody. Much apprecited.
Yeah, I don't know if you guys, Roger or Jean, did you have any closing remarks you want to make for this presentation, or?
Thank you for patiently listening.
Okay. All right. Sounds good. All right, Simon, are you ready?
Yeah, mate. Yeah. So, Roger, Jean, that information you showed is really, really valuable to us. Like everyone else on this channel, I've been chasing my tail trying to understand oil and gas for some time now, and trying to get clarity has been really hard. So thank you. And I know it's professionally risky to publish stuff like that. Or it can be. Yeah, so my compliments. So, all right, so where is my share button? Start screen sharing. Share and... Okay, let me know if you can see that.
Yeah, we can see your whole screen, so you should be able to go into presentation mode.
Okay, so, so it's in presentation mode now, right?
Yeah. Mm-hmm.
Okay, all right. So what I'm going to share tonight is, after much ado, the Hawaii report, which took a while to get out.
How long have you been working on it?
Well, that's an interesting question. The project's been running for about 3 years.
Mm-hmm.
But it didn't take 3 years to do, because in that time my computer was hacked and destroyed twice.
Oh, wow.
There was several times that we had to start from scratch again. There was also a point when the information we got from the Department of Transport was wrong, fatally so. And that had a ripple effect through that. And so we had to do 2 parallel simulations to try and get some sense out of this. So it's had to do many times, but out of sheer persistence, we got through it. So there's probably, I don't know, maybe 18 months work here, but it was spread over 3 years. Right, so why Hawaii? This is the 4th in the assessment series, and I get asked a lot. So the question is, what's a sensible plan to phase out fossil fuels? And so the idea was to look at the green transition. If the conventional plan won't work, what might? How big is the circular economy, and how does it relate to the green transition? That's never been done. So what kind of resources do we need, and what kind? And so this is the 3rd in the assessment series. So the original plan was to do one of these for each of the Nordic countries. Behind this, for example, I was of the opinion Europe would struggle to stay Europe. It actually might break up. But what will take its place is a series of new power blocks. And I could see the Nordic frontier coming together: Finland, Sweden, Norway, Denmark, Iceland, and Greenland. Because they preferentially do business with each other because they understand each other, and the cost structures are very similar. And so the idea was to develop methodologies that were different than the Northern Hemisphere. Go somewhere completely different. It's also an island. The Hawaiian island chain is isolated, so it can be modeled as a system more easily. It's got geothermal energy there, so it can mirror Iceland. And I wanted to also get certain things on the ground and modeled, so by the time I approached Iceland, certain things were actually in place already, which means that the Icelanders might be more agreeable to certain things being done. That was the plan. As it turns out, this study in Hawaii is probably going to be the last of these. Well, I've moved into a different department now, and they're getting me to chase different things.
Oh, okay.
So, like, for example, I'm now chasing China, which is a different animal.
Also very interesting.
I have no idea. I've picked up on a pattern for that, and if you've got the minerals for it, we can talk about that in another podcast. But it's actually a very important resource story that crosses into all sectors. Anyway, so back to Hawaii, where they put pineapple on pizza. Or do they? Anyway. Anyway, so Hawaii was very dependent on fossil fuels, oil in particular. To generate electricity, they burn oil. Right. So also they're very dependent on the economy is not based on any industrial commodity production. It's based on the tourism industry. So if there is a supply chain problem, and it's got a very long supply chain, and any disruption in the oil industry, this community is snookered. Right. So also, when I was actually writing reports about the Nordic country in Finland, I had this sort of tendency to be polite to the locals because I wanted to work with them. Whereas in Hawaii, I felt I could tell it how it is. And if I offended the locals and they told me to go away, well, I could go away and still work with the Nordic frontier. So there was an element of that. Right, so this is the actual report. That's the link there. It's public domain. So what you've got is the main report, which is 691 pages, plus 2 volumes of appendices. And because the link can only do one report, it's all been put together. So when you download it, it's 1,400 pages. Sorry about that, but that's the only way we could get it all up. When they print it out in Hawaii, it's gone to every sector in the Hawaiian community, and the Hawaiian Senate, the U.S. Navy, Department of Transport, they're all looking at it now.
Wow!
And so we printed it as a 3-volume set. This has actually got a set of solutions in it. So the idea was as follows: we wanted to get every single problem and challenge, document it, database, put it all on the table, all at the same time. Then on the same table, we would have put all solutions, conventional and unconventional, back them with data. Around that table is all stakeholders, so we can have a frank discussion. It was written for 2 reasons. It was written to model certain ideas for the rest of the world, but every author on that list is Hawaiian, apart from me. Right, so this was written by Hawaiians for Hawaiians. So I'm hoping they will take this report and have a frank discussion about what to do going forward. Right, so what we looked at...
Harold is Hawaiian? Harold Sverdrup?
Say all that again?
Harold Sverdrup is Hawaiian?
Sorry. No, Harold Sverdrup is Norwegian. Sorry. So not everyone was Hawaiian.
Just wanted to...
He wants to be Hawaiian. There you go. He actually wrote in the appendices. There is an appendice written up on the Easter Island game theory. He wrote a game theory analysis of what happened on Easter Island. He also wrote a series of appendices on the energy consumed in mining of metals and everything, and so he contributed multiple parts of the report. But everyone else lives in Hawaii. Right. So there were a series of scenarios, and they were to look at everything: green transition, hydrogen economy, biofuels, the ammonia fuel. Even though some of these things were not, we're considered to be, we've moved on past that. There's still a number of people that still absolutely believe in some of the older solutions. So the idea was to put all data on the table for all people, which means everyone can take part. Also, the first 4 scenarios could be used as to make your own energy mix going forward. I looked at a few things: the green transition, circular economy. If I looked at degrowth, if we were to contract the Hawaiian economy by 40%, what would that look like? The one that Andrii is very interested in is scenario H. It's HH.
Yes. I'm very happy that it was included.
Because of the problems that we actually had, that was the last one, and that would have taken a bullet if it actually if things got to. I'm very glad we did it though. If 100% of food was produced for the number of people there, what would it be based on the hamlet design and using organic regenerative permaculture? So I've got the numbers for that to show you. Also the purple transition. So this is the unconventional scenario I put together. Thorium molten fueled thorium-fueled molten salt reactors, plus a series of other technologies. And if some of the ideas that have been promoted by the Venus Project, for example, were tapped into, like resource balanced economy. All right. So a bit of history here. So this was the 2021 report that looked at the global system. This was the Finnish assessment. And then this was the global calculation that went into a peer-reviewed bulletin, the GTK bulletin. So it's been peer-reviewed. And again, this took 2.5 years to get through peer review. So this work has taken a long time to get through. All right. The paradigm is this. Map the state of Hawaii for 2019. We're going to fully electrify the whole system. Fossil fuels is wiped out entirely. We're going to keep electricity generation, but we also want now passenger cars, trucks, vans, buses, what have you, domestic maritime, international aviation. All fossil fuels systems are gone. So, but we need to maintain the same capability. How are we going to do that? We model for 1 calendar year. I've used 2019 because this was the last year before the COVID pandemic supply disruptions came. During that era, a lot of data surveys just stopped. And a lot of them haven't recovered. They haven't started up again. At the same time, there's some data artifacts that are really weird in the system after that. But if we're trying to model how society actually is when everything's stable and normal and all that, 2019 was the last year to use. And yeah, that was the decision made. Same physical activity, same mechanical work done, same distances. Assemble all data for all practical options. The ideal would be all problems and challenges are data mapped and referenced, placed on the table along with all possible solutions, conventional and unconventional. Around that table, all stakeholders are present and constructive dialogue then commences. And as this is Hawaii, it's really only the people in Hawaii who should have an advice, have a voice, and everyone here else are advisors. That was, how I see this. So electricity generation. This is the power generator. Now remember, this is an internal combustion engine economy, and they don't need to heat their buildings, so their power generation requirements are actually relatively low. That being said, a lot of it's either petroleum or coal. They did have a bit of wind, they did have a bit of solar, but and this petroleum, this oil, is coming from Russia and Libya. It's not even coming from Alaska. So they do have a vulnerability there. It's transport. So this was the number of vehicles. Now, we looked at the number of vehicles, but we also looked at in terms of the consumption of gasoline. There was a bit of confusion in the data in terms of what vehicle classifications were what, and this was what caused the problem, especially all the heavy vehicles. So 36.9 terawatts of thermal energy and 6.2 terawatt hours of mechanical work done, and for a population of 1.4 million people in the year 2019. So we went after the number of vehicles, and there were 1.279 million vehicles, and then you had a number of trailers on top of that. So this was the number of miles. Now, there was an effort to have units in imperial miles and metric kilometers and meters as well, and to double up. So anyone can use the report. But if it's going to be for Hawaiians, it has to be in a language they understand. This is all right. So fuel consumption, this was the fuel, the tax base, what was actually consumed. Okay, great. And these are the scenarios. So status quo, no change. Scenario HA, everything's electrified. And for HA to HD, we looked at if there was exclusive solar power generation, exclusive wind, exclusive hydro, and so on. And that was to look at, they're like boundary conditions. It's not practical. They wouldn't actually do any of that. But what you can do is assemble parts of those technologies to make any energy mix you want. It was also to talk to people who were very one-eyed about what things should happen. Like I came across quite a few people, for example, that believed solar power is the only thing worth considering. Everything else is a waste of time. All right, here's your data. Electrification, hydrogen economy, HC, everything's biomass or biofuel. There's the belief that nothing else is worth talking about because we can grow more biomass. Well, how much biomass are we talking about here? And that's where things fall over. Ammonia is a fuel that's sort of come in. It's been considered. It has its place. But there is a school of thought that believes that everything should be ammonia fueled. Is that the case? Let's have a look. Especially when you've got to make the ammonia. Right. Then we looked at scenario HE hybrid 1. This is the green transition. The energy split proposed by the IEA based on existing Hawaiian regulations. They won't allow, for example, a nuclear power plant to be installed. Meanwhile, they've got lots of military ships in the harbour with nuclear power reactors in them for the last couple of decades. So they also won't allow the expansion of geothermal power. They do have some geothermal. The indigenous population on Hawaii see the volcano as a religious deity, and so geothermal is considered a no-no. So there's a few things to talk there. The idea was to put the data on the ground, though. So this is the regulations as they are now, number one. Number two, if they were to evolve those regulations and they were to allow certain things with the technology that's available now, what could happen? And so this is, for example, the implications of installing a single nuclear power reactor, light water reactor, into the Hawaiian system, and what would that change in terms of required infrastructure? Because nuclear is very reliable, but solar had only a 19.2% availability. Hybrid 3, we're going to take HE1 and contract it by 40%. Right, so this was a tip to the hat to the Club of Rome limits to growth idea. I initially had a steeper contraction, but I was convinced to actually keep it at 40% because it'll scare the punters if we do too much. Scenario HG, 100% recycling. This is circular economy. Everything's collected and recycled. All right, if we did that, what would it look like? Scenario HH, sustainable regenerative agriculture. All food is produced with regenerative agriculture and permaculture principles, no petrochemicals. And so that was mapped out. We'll spend a bit of time on that. And then there's the purple transition mapped out in full. And there's a number of appendices associated with all of these. And Appendix 1 is all the supporting data. Appendix 2 is when we start looking at the unorthodox solutions. And everything is referenced and it's public domain. This report was been written for everyone to use. All right. So existing electrical demand, gasoline-based transport, diesel-based transport, domestic maritime shipping, international aviation, and away we go. All right, I won't belabor the point. We've actually already talked about all this. What happens if we have no action? I just wanted to put that in a report. I didn't.
Yeah.
All right, scenario A, boundary condition, all systems are electrified. All transportation was electric propulsion, powered by lithium-ion batteries as per what they think they're going to do. All conventional on-fuel power systems were looked at. And it was found it was more sensible to have a combination of technology transportation systems. Not rocket science, but this is what the conclusion was. So this is what we had. So transport allocation, this is the calculation. How much gasoline and diesel was consumed? What's the thermal energy content? What is the energy transfer efficiency? Like gasoline's 21%. But when you actually come out in terms of useful physical work done, electric propulsion systems are 73% efficient. So we go from 21 to 73. There's a big saving there. So then that works out the amount of electrification that's required. And then we got to a local renewable energy consultant called Azimuth Services to help us, as in if we were to actually install solar panels in Hawaii, what's the state of the art, how would things go, and what are the efficiencies? And this is what we came up with, and you end up with 31 terawatt hours. So this is solar. This is the Azimuth simulation that was done. So we looked at, well, we need this amount of power, 31,205 gigawatt hours. So we need to deliver that every year. So if we're going to do that for solar power only, how would we do it? So where could solar panels be installed in Hawaii? And so we assumed a fraction of the energy mix. In this case, it was 100%. And we looked at a series of different systems, like solar panels on houses, like commercial civilian houses, like family houses, commercial rooftops, parking spaces, fixed tilt, ground mount, and single axis tracker mount, and each one had a signature, an efficiency, and the guys that did this collected data from Hawaii itself, solar radiance data from the island of Oahu for each of these systems. So then they worked out the installed wattage per unit, and to deliver that amount of power, we need 18.57 gigawatts, which is 41 million solar panels. From that, we also worked out if we were to deliver this all the time, in the solar radiance is different in winter versus summer. There's a dip, which means there's a shortfall, and we worked out the size of that shortfall. I'll show you that in a moment. So here is the specific yield data across the month, based on solar radiance in Oahu. And so this is what, in terms of, for every installed kilowatt, how many kilowatt hours will be produced per month? So this is actually quite good data. And then from that, we will work out, well, okay, how many installed systems do we need to actually hit the target of 31.2 terawatt hours? And so when we graph that up, this is what you end up with. In winter, January, February, November, December, there is quite a bit less solar power. This is Hawaii where the sun shines pretty well. And so if this was a standalone system, the dotted line would be the average, which is what we can deliver all the time. Anything above the dotted line should be captured and stored to fill in what's below the dotted line. And so this area here is our buffer. And so this is the amount of power that actually was brought in. This is the shortfall, the minus. We summed it up together, and it turned out to be a little under a month. So we had an availability across the year of 19.2%. And this is in Hawaii. The global average was actually 11%. So across the year, we had a shortfall of about 1 month of capacity over sustained 5 months. This worked out to be 28.8 days of power storage that would then have to be kept for about 5 months. And so the whole issue of should the power buffer be there and how big should it be? There it is, 28.8 days in Hawaii. So imagine what it will be in Northern Europe. Okay, so I put this example of what happened in Spain recently, where this is what Spain at night when the grid works well. And a couple of, on 28th of April, they had their power blackout. I'm assuming everyone on this call understands all this. This is the data. This is the data that actually of what actually happened. So that yellow line there is demand. And when they had the blackout, they had more than enough power. The problem was there's a big chunk of solar here. They had a lot of extra power coming in, and the frequency changed. And that frequency change required the grid to shut down for its own protection. But once it shut down, then they had the black start, and then hilarity ensued. This puts to rest the idea that if we just had a 3 times build out of solar and wind, that will negate the need for storage.
So could you explain what the frequency change? I'm a little confused.
Okay, so the power when it comes out of our technology has evolved when we are burning fossil fuels, where we control the amount of current and the supply of it. Current, voltage, and what's called frequency. The sinusoidal voltage plot as it goes, the frequency moment of that, it's 50 hertz. It's supposed to be 50 hertz, but it's got a very narrow window. If that frequency changes even a little bit, right, the system can't cope. And you've got the equivalent of a power surge running through your computer. So the moment a frequency change, and it was actually quite a big frequency change, far more than the system can handle, the equivalent of a circuit breaker kicked in. I think it was 2 systems kicked in, and then the whole system just shut down. And once it shut down, they had what's called a black start to start it up again, which was really problematic. So that this is the actual whole point of the exercise of looking at this. Right. Scenario.
Dan has a
question. I can't see the question, so you have to read them out.
Dan?
No. I was just making a comment that the the frequency dropped from 50 hertz down to 48 hertz and was going toward 47. And that was enough to trigger basically a break in two pieces of equipment. And that triggers a cascading event. And that's the basis of the brass paradox. As it becomes complex, it becomes unstable. And you get these cascading failures. That's all I'm saying.
Yeah. So,
Well, Simon, you're on target. That's what I'm trying to tell you.
And I'd just like to add, as I understand it, the individual solar things are designed to track the main cycles. And when the main cycle gets a little bit out of whack, then they will home in on that cycle and causing more of the machines to be malfunctioning. It's a really interesting positive feedback. Graham wants to speak, apparently.
Okay.
Hi, Graham.
Oh, g'day. I was just going to add a comment about frequency. Basically, frequency basically tells us how supply and demand are tracking. And so there's various set points in the system so that when the frequency drops below a certain point, it means that basically supply has exceeded demand. So there isn't sort of something that, for example, if the frequency drops to 48, it doesn't mean everything literally explodes. It simply means that supply has exceeded demand and that something needs to happen. And so there's various set points in the system that are set at different frequencies to react to that. So frequency is in effect a proxy for the supply-demand balance.
And that balance has got to be the same to a millionth of a second to be managed.
Well, it doesn't have to be. I mean, in practice, there's various systems that work at different time intervals. So, for example, there's a 5 second, a 1 minute, a 5 minute, in effect, market to shift the supply-demand balance. So there isn't literally, the timing isn't a critical factor in this in terms of a microsecond or a second or whatever. So, for example, in the Australian market, there's a 5 second up and down market, there's a 1 minute up and down market, etc. So these things are basically designed by engineers to provide a gradual, controlled way of managing the system when the system isn't working properly, so that basically the system doesn't crash in one heap. You basically have a gradual unloading or loading as is required. I don't know whether
Andrii, I've got a lot to get through. Can we keep?
Yeah, sorry. Okay. Back to you, Simon.
Yeah, look, I'm sorry to cut you off there, but I'm not going to make it to the end if we're going to do it.
Okay, sorry. Okay.
All right. I agree, by the way, but yeah. All right. Scenario HB was hydrogen. Everything's now a hydrogen fuel cell, and the annual quantity of hydrogen required to do all this. And then we also looked at all the different power systems. Scenario HC, all systems are biomass supported or biofuels. All electrical power is delivered through combustion of biomass. All internal combustion was now with biofuels. The quantity of biofuels needed and the area of arable land required to annually grow was calculated. It was found that the required area to grow the biomass feedstocks, so for conventional feedstocks, wood, corn, and soybean, far exceeded what was possible. And so while all non-fossil fuel systems have their place, they have a fit-for-purpose application. The large-scale application of these biofuels won't work. What might work is if you looked at an unconventional product, which I modeled, which I'll talk about shortly. Right. Ammonia. All internal combustion engines are retrofitted to be fueled with ammonia. First, you have to make the hydrogen, and then you have to make ammonia from that, how much we're talking about. And then we actually did the same thing before with so this scenario proved to be the most energy intensive by far. So ammonia is a useful fuel to consider in the final analysis, but it's not for all applications. It's a fit for purpose thing. It may be the most practical way to maintain international maritime shipping industry, but it has its problems. All right, the green transition, H1. So the green transition as advertised, all short-range vehicles were electric vehicles. All long-range heavy vehicles were considered to be hydrogen fuel cells. Power generation mix was proposed by the IEA for 2050, so where solar and wind take out 75% of the energy mix. What we used here was because of in Hawaii, they would have to actually sort of do it a different way. It was solar now took 80% of the energy mix, which is what they thought they were going to do. And a logistical limitation was shown for the needed stationary power storage to meet for that, given the 28.8 days calculator. Now, what would happen if we change regulations? Well, so we'll take scenario H1 in terms of the amount of power, but can we deliver it with different systems? So the installation of a conventional nuclear power plant, what would happen? Scale up of geothermal power, the application of wave and ocean energy systems, and the application of a specially bred perennial grass species to use as feedstock for biofuels. It's about 7 or 8 times more effective in prolific growing of biomass than corn. So then this came to the whole idea of, well, the amount of metal we would need to do this on a global scale far exceeds the metal we've got. So this is actually the study that's come out of the bulletin. This is to show that the market's going to be inelastic. The idea that you can just go out and buy solar panels and batteries and that's not going to happen. And Hawaii is a very small economy. Moving on, right, resource depletion. To model a 6-month disruption to maritime shipping and aviation imports, Hawaii would have to become more self-reliant and have a smaller footprint in resource consumption. And the system was contracted by 40%. This is a tip to the hat to the limits to growth idea. If you were to start to contract the system, what would it look like? Circular economy. The performance characteristics of a network of recycling plants in the United Kingdom were taken to estimate the mass. So we took the mass of rubbish generated in Hawaii and we recycled them all. And based on that performance, we estimated the volumes and type of materials that could come out of that. Now, so there's very little manufacture in Hawaii. So the idea of a circular economy is not practical. So the idea is all the recycled stuff's put in a ship and sent to Southeast Asia, which can be inserted in the manufacture chain. Of course, that assumes that's worthwhile. In practice, what would probably happen was manufacture would evolve in Hawaii in a very small scale in a much simpler fashion. Purpose of this, though, was we can now compare the green transition to the circular economy in terms of infrastructure. I'll show you that shortly. But it was observed that the infrastructure required for the green transition was orders of magnitude larger than was needed for the circular economy. Now, when you hear people talk about this, they often refer to them as if they're the same thing, or it's given that the other one's happening in the background. They're actually 2 different tasks, and one's more important than the other in terms of what it does for society. So what is this? All right, so this is the linear economy, where natural resources are extracted from the ground, turn it into stuff, and then we put it in the landfill, throw it away. This is what Hawaii does at the moment. So imports coming in, we've got consumption, we export some stuff, and then what goes into landfill. The stuff that's diverted is the stuff that's actually being recycled at the moment. Okay, so the circular economy, won't go through that. I'm assuming you know what this is. Right, but here are some cool graphics I put together that show what's happening here. Circular economy, take stuff, recycle it, reuse it, so we can actually reduce the amount of stuff being extracted from the ground in the first place, and we reduce the amount of stuff we put in landfill. So in the mineral intelligence world, we're talking about aluminium and copper in a pure form, but once it actually goes into these things, it's actually sort of braided into all, like a smartphone's got many materials in it, and they're so integrated and they're so micronized that you can't really recycle it effectively. So it's just throw it into landfill, throw it into the furnace. And so we've got this idea, well, we start with a mineralogy and we go through a process extraction, and you end up with a metal or a refined chemical. But then that goes to a trading platform. And and then you go to the next layer of business. And so then you have another metal markets trading platform, and then that gets sold and manufactured into finished goods. Then that gets distributed, and then it goes into the waste plume. And this level of complexity just doesn't seem to exist in any of the circular economy discussions I've come across. We talk in circles. So this was the model for Hawaii. Stuff's made, let's say it's Southeast Asia, brought in a ship to Hawaii, we consume it, we recycle it, and we put it back in a ship to send it out to be valorized. Of course, this isn't practical, but it was a simulation to actually prove a point. So this is the mass flows of what the circular economy could be if we were to catch everything. So waste generated, that's the recycling that could come from it in terms of performance of existing recycling plants. So some stuff goes into landfill, but it's much, much less. But we've got all this other useful stuff that might be useful elsewhere. Also, in the circular economy, I put in a few other ideas, like Appendix Mu. This is one of the appendices. If we were to take rubber tires and put them into a pyrolysis plant where we're heating it without oxygen, it breaks down to a fuel oil. One of the products is fuel oil. And that fuel oil, after distillation, a series of distillation steps, could be a substitute for diesel fuel. So Hawaii produces around 750,000 tires a year. And from that, we could make something like 580,000 gallons. Now, that's nowhere near enough for to substitute oil, petroleum products, but you could do something like run emergency services off a waste product where they control it outright. So also, if we take sewage and put it into a pyrolysis plant, well, this amount of sewage that's been produced by Hawaiian society, you could make 2,600 tons of syngas. And that syngas could then be used for a variety of things. You use it for cooking gas, but you could also use it to recycle iron powder from the purple transition. The other idea that was in the circular economy was to look at plastics. There's a great big gyre of plastic in the ocean that's really near Hawaii. It's the size of Texas, it's 30 feet deep, and it's a big problem, and everyone's pointing at everyone else. So I propose this. Take an oil tanker, rip out some of the oil tanks, but not all of them, put in a pyrolysis plant and a processing plant that sorts and cleans the plastic, and have it fueled by a thorium reactor. And if we just if we had like 4 systems running in parallel that looked at plastics of different densities, we could pull 40 tons of plastic out a day. So we're making something like 5,400 gallons a day of diesel. You bring the fuel oil back to a refinery at port. What this means is one of these ships could go up and down this gyre like a lawnmower, stripping plastics out of the ocean, and it would clean that gyre up in about 6 years. And again, it's not enough diesel to replace diesel consumption at the moment, but it takes an environmental problem that's quite serious, turns it into something we can use. So we solve 2 problems at once. Mm-hmm. Right, so here's the infrastructure. Circular economy. So if we had all these recycling centers and pyrolysis plants, we're talking about 53 facilities of various sizes. And some of them are what you would call pilot scale. That's the circular economy up the top. And that is actually most of the discussion that you hear in sustainable circles, saying European Commission talks and stuff like that. Okay, great. Now here's the green transition. So you've got electric vehicles and all the transport stuff. Then you've got the power generation stuff, like 28 million 450 watt solar panels, 275 wind turbines. Stationary power storage is huge. 3,390 storage sites that's actually up at the moment. They've got like this 565 megawatt capacity battery bank that's up at the moment. And they think, hey, this is great. And they need 3,000 more of them. So what you've got here is up the top, 53 facilities to do the circular economy versus this massive laundry list for the green transition. Now, the green transition, while it's so much larger, it's also more important. Energy, transport. This is the stuff that holds society together. In the hierarchy of needs, the green transition is far more important than the circular economy. So they need to be quantified. The relationship between the two needs to be understood. And whether you can, it's even viable to actually catch all that stuff and recycle it is another thing. And in the current system, the answer is no. Right. So now for stationary power storage. So you've got scenario hybrid 1, hybrid 2, and the contraction hybrid, 40% contraction. This is the amount of gigawatt hours of power storage will be needed. That difference there between the red and the yellow is what happens when you install a nuclear power plant. And purple doesn't need any at all. So this is installed capacity. That's the amount of power has to be stored. So again, you see this big step down. And this is the Carpoli energy storage system that's in place at the moment, 565 megawatt hours of battery storage on Oahu. Now, it's a big storage plant, and they're all very proud of it. Now we need 3,000 more such sites like this to do the existing regulation system the way they think. And that's actually the Achilles heel of the existing system. All right, now this one's for Andrii. Regenerative agriculture. Okay. So regenerative permaculture, sorry. Scenario was developed to examine the question of what would be needed if the entire state of Hawaii sourced its food from completely organic sources. All petrochemical fertilizers, herbicides, and pesticides were phased out completely, and only organic systems are allowed to take their place. Paradigms to be examined were regenerative agriculture, permaculture, and food forest agriculture. A model was developed to assess what kind of arable land footprint a community of 200 people would require in this context. This is Andrii's hamlet. If you made a hamlet as the unit, what would it look like? How much would it need? I got it. It's since been reviewed and everything like that. This was it was then projected onto a map. So if this is the amount of land that we need for 200 people, or how many hamlets will we need to actually have in terms of the Hawaiian island chain of what's there against the arable land of all kinds. Okay, so now let's look at some data here. This is all scenarios together in terms of annual electrical power. On the left, we've got, this is what happened in Hawaii in 2019, where that's just electrical power. Everything after that looks at electrical power and transport. So the four boundary conditions, A, B, and D, are just so massive. They're not practical anyway, but that was the data. And scenario C is the same capacity as the existing system. So let's take out those three there, and that's our data. This is the same data, but we're going to take out the hatched columns. So there is 2019, the way it is at the moment. There is HE1 with, if they were using existing regulations, HE2, this is the amount of power generated. And this is the contraction, and that's the purple transition where you've got, the purple is thorium molten salt, and the gray, and the brown is geothermal. Now, here's where it gets interesting. That's the amount of power on the left. The installed capacity is on the right. If we were to do this according to the regulations green transition, we're talking 15 gigawatts of installed power generation capacity. But look at purple. Purple is down at actually this should have a little bit on top of that. It's actually a little over 3,000. This is an old chart, but it's actually a little bit less than the existing power generation of fossil fuels at the moment. It's a little bit less. So what that means is we can not only decarbonize and phase out fossil fuels, but we can do it with a smaller footprint than what we've got now. And what's allowing that to happen is thorium molten salt reactors. It's much, much smaller than anything conventional. In terms of land area to grow the biomass, HC, where we're going to look at all the biomass, that's huge. It's off the chase. The land area of all islands of Hawaii is the white rectangle on the right. And this is the amount of arable land. So that's not going to work.
Mm-hmm.
So what are we taking out? We're taking out HC. All right. So now we've got HE1 with conventional systems. It's still way too large. So we've got the total forest area of all islands. The total existing arable land in farms is the brown, and the land area of the entire island of Maui. So HE1 with existing regulations, that's not going to work anyway. So all the biofuels from conventional systems just isn't going to work. But when we go xanograph, which is that perennial giant grass, which is essentially like an evolved sugarcane, it's been crossbred. It's not genetically engineered. It's been crossbred to be the way it is. All of a sudden, that's more agreeable.
So it's a better biofuel?
It is a better biofuel. Now, it's a new product. Now, the company I talked to did share me their research data. What I've advised the Hawaiian government to do is to do their own independent test and see if that is actually, in fact, correct. Mm-hmm. And if it is correct, that's how they keep the aviation industry going. Just the aviation industry, internet, because Hawaii becomes a refueling point.
Mm-hmm.
It's still not enough to do everything. You've got to have like a combination. All right. So what have we learned? Conventional thinking won't work. All conventional strategies to phase out fossil fuels have a logistical scale-up bottleneck that make them probably unlivable and unviable. So when the orthodox convention fails, turn to the unorthodox and accept the unconventional or accept failure. Right. So that's the first. All existing plans won't work. Turn to something else. So now we're back to HH. This is actually the results for HH. So Andrii, you've got the credit here. This was actually developed after listening and talking to some of your ideas, and then I went away and researched them.
Mm-hmm.
So what I started out with is, what was the diet for a single person? What's a recommended healthy, balanced diet that can come from organic processes? And worked out in terms of kilograms a year, how much will we need for one person, and then how much will we need for 200 people. So this is the diet requirements per food stock. Okay. Mm-hmm. So then I went through a series of these things here. So we need, where's pork? Pork. So we need 2,400 kilograms for a single hamlet a year of pork. So 2.4 ton. So 2.4 ton is the black there. How do we get it? Mm-hmm. And so we calculate backwards. Well, how many piglets need to be? How many pigs need to be slaughtered a year? And then what's their growth cycle? What do they need so they can be mentally healthy? Free range grazing. The pigs themselves have to be fed. What feed? And then you have to grow that feed. You've got a breeding herd, and you've got a meat herd, and there was a mass balance accordingly. So I went through this process for everything in this table. It's all in the report. Mm-hmm. So there's sweet potato. So how do we get 12 tons of sweet potato a year for 200 people? So then I went through what was the arable land required to grow 1,000 kilograms of a target food. So how many acres of arable land based on this kind of analysis? Okay, look at this.
Yeah.
This is what they were, when you hear people say we should go vegetarian, this is actually one of the arguments being used. Look at beef. Mm-hmm. We're up at 30 acres, 30-something acres. Pork is not far, is better, but not by much. Dairy products, poultry, meat, eggs, they're much better. But so if we take out those beef bits at the end, so what do we take out? We've taken out beef, and we've kept pork. Okay, so now we've got like number of acres. Fruit, rice, corn, sweet potato, that's all manageable. And so, poultry, meat, eggs, look, it's the land that it's taking up here, and that land needs to be managed. So I came up with, for a 200-person hamlet, we need an annual footprint of 108 acres. Now, this is just growing land. You need arable land. You need fallow land on top of that, which is coming shortly. So the problem here was to make enough nutrients to make fertilizer, the nutrient balance. That's when the trouble started. And so you have to get nutrients from outside the system. So there's going to have to be whole farms of fertilizer production, and their job is to make fertilizer production to get all this to balance. So then, if we were to take the idea of this, and so here's a hamlet, and we have different areas that did different things. There's a food forest on panel 13. We've got old growth forests with a couple of ponds, but also there's a couple of beehives in there, and the beehive's sole purpose is to maintain the fertilizing and pollination of all other plants. That's their primary purpose. So that was the layout for what's called season 2. So what is season 2? So there's 4 seasons of the year, and so we've got this idea of crop rotation, where the land can go fallow. So when we have a crop running, okay, you're on a crop, but then you can't just keep cropping. You got to let the land fallow, and you've got to fertilize it. And then you can have chickens grazing on it, and goats and whatever, and the animals grazing on that land will fertilize it. Then you send in some pigs. Now, pigs are quite destructive. Pigs need grazing land. So instead of plowing the land, we'll get pigs to graze it for a bit, and they'll destroy everything. And so that's actually a substitute for plowing. Pigs are amazingly destructive, but the mental health of all these animals needs to be maintained, or we don't do it. Right? So it all needs to get it to balance out. So this was the nutrient balance I did for this was nitrogen. So this was the amount of rice, corn, soybeans of what we need. How much nitrogen do we need? We need to supply them with nitrogen. And the right-hand side is where do we get it from? And so these are the sources of nitrogen and how much mass that we would need for each one. So I went through that process. This is all for a 200-person hamlet. This is phosphorus. Same process.
Oh.
And yeah.
And did you include human manure?
Yes.
Okay.
Yes, I did. Human manure, though, wasn't used here. It was used to make syngas for another part of the system.
Oh, I see. Okay.
Right. So you can use human manure here, but I chose to use it in another part of the system. So this was organic agriculture merged with industrial sustainability as well. This is potassium. Same basic pattern.
I was just thinking that after you get the syngas, you still have the minerals.
Yeah.
Yeah.
And so
you could use it for both.
Again, yes. Okay. So this is a very simplistic study. It's just scratching the surface. So now we've got a 200-person hamlet. This is the amount of arable land that we would need. This is the amount of food we're going to produce, and this is the organic fertilizer that we would produce, where some of it happens off the hamlet. And this is the size of the system we're looking at. Okay. All right. So what happened there? So this is actually, hoping, no, oh, sorry about this. This is actually a, the arable land, let's say 200 people is a single hamlet. How many hamlets do we need to match the resident population of 1.4 million people in Hawaii? And that's this column here. This is all the land used for that. The purple is land fallowed. Right, so we've got about 33% of land fallowed. So this is the idea that you can have fallowed land. So if all that was summed together, on the right is a column of arable land currently in farms across the islands, and they match. So what that means is, without actually going and making new farms, and there's plenty of extra land, but using what you've got now, of course they'd have to let go of all their cash crops, which will be a problem. But this, in theory, is possible. This is showing it's possible. They could go completely organic if they had to. This is Hawaii. Good luck doing that in Finland. But yeah.
Mm-hmm.
All right. Now, do you have any questions, Andrew, before we move on?
Oh, well, I was just thinking Finland is bigger and you can do pine nuts and pea shrubs but
coffee. Coffee.
Well,
no
you can't grow
in
coffee
Hawaii.
in Finland.
Coffee, no coffee in Hawaii. No.
Well, this is what they grow a lot of in Hawaii at the moment. So I took out all those cash crops, but of course reality will be different. But this is to show, in theory, it's possible, which means they can have a negotiation and work out what to do, and they'd have to do a more sophisticated study that would actually include more and balance more and all that. All right. So moving on. So what are we really trying to do in terms of industrialization? So this is how do I fit HH in with everything else? So we want electricity, we want transport, manufacture, we want reliable, consistently stable power generation in a concentrated form, where we can send concentrated amounts of power in to one site, low materials footprint, a long working life for each unit, like 40, 50 years. And when they do come offline, they're designed to be recycled with a minimal waste plume with a very low environmental impact. That's the laundry list. So if the green transition won't work, what might instead? I present scenario HI. Purple transition is now documented in full in the same way, like this. So the resource balanced economy was looked at. So if we actually looked at how our resources were captured and managed differently to the different paradigm to what we're doing at the moment, this is actually an evolution of the circular economy. So what I've done here is I've taken Jacques Fresco's resource-based economy and added energy terms. So I call it the resource-balanced economy. Look up the Venus Project if you want to chase Jacques Fresco's work. Liquid fuel fission. This is the thorium-fueled molten salt modular reactors. I actually did a deep dive on that and did a full systems analysis. I also calculated the energy return and energy invested on the whole system, which was quite extraordinary. Electric vehicles now powered by alternative battery chemistries, but we still need some of them. Combustion of iron powder to replace coal. So we have a metal fuel that does the high-end heat, like 2000 degrees centigrade. But that iron powder could be recycled with syngas produced from human sewage. And also, now that we've got a standalone heat source, we can now look at the sulfur iodide cycle to produce hydrogen. And ammonia-fueled ICE technology to maintain the maritime shipping industry. Hawaii, for example, could make ammonia to refuel ships. It could grow the xenograss product on some of its land to maintain the international the aviation industry, and the rest of them could be self-sufficient. And that would be the reason to be for Hawaii Post. Right, so I won't go through this. I'm assuming, Andrew, should I go through this, or is it assumption that we've already seen it?
Yeah, we've seen it, I guess.
Yeah, okay.
And I know you were limited for time, so
yeah. So rock and roll, pass through this. I can give you this presentation if you want. I did one of my contacts in the Department of Energy in America made this request. For a gigawatt of electricity, do an assessment and compare an advanced light water reactor system based on the AP 1400 light water reactor up against a thorium molten salt reactor per gigawatt of electricity. And so the massive reactor fuel, I had to put them on a log scale so you could even see them. The thorium system is orders of magnitude smaller. Now, there's a whole lot of these, but this makes the point. Step through that.
I just had a question about that in terms of the availability was only 75% for MSR. Was that just kind of an additional constraint, or?
Nope. No. So that's the published data. So the reason, so that's based on the Fuji system that was in Japan. 75% is what they ended up doing. It's a research reactor, so they kept shutting it down to do research experiments.
Okay.
A commercial reactor up and running will be probably the same as a light water reactor of over 91%. Copenhagen Atomic believes their system is robust enough and stable enough because it's a much simpler system that their true availability could be as high as 98.
Wow.
But that's so again, you've got to scale at 75 to 98, but that's the published data. Step. This is the size of the system. It arrives on a truck like a shipping container. 50 years of fuel have loaded in it, and away it goes. There's me standing in front of one of these systems. This is a test system. Now, the business model behind Copenhagen Atomics is they're going to lease you the reactor. They're going to make one of these a day in their factory in 2028, if all goes well. If everyone got out of their way, they could be making reactors next week. What they saw, that they are perhaps the most advanced in the world at what they're doing. They're producing electricity at 2 cents a kilowatt hour. There are other operators. Like I was contacted by someone who claims that they'll be able to do with their system 1 cent a kilowatt hour. So it's going to be much cheaper, than what we're doing at the moment. And that was something I didn't expect. Okay, so last thing before we move on, I actually came up with an idea of we need a new form of transport. When I actually did the assessment of phase out fossil fuels, where's all the energy going, trucks are taking a massive disproportion of the energy required post-fossil fuels. Now, we can't just stop trucks. Trucks run our society. A very nice book was written by Alice Friedemann called When Trucks Stop. She's written a couple of books. That's a really good one, When Trucks Stop. You can't just take trucks out. We've got to deliver to society what trucks do without trucks. That's the challenge. So I'm going to present you an unusual idea. So here's a comparison of, say, a bus of 90 passengers versus 50 cars and those passengers. Okay, and you have bicycles in between. So if we were to put them all on a monorail, and instead, so this is the metrics of what would we actually do. We know what monorails are, got the technology for them. There's a technology that was sent to me by a group in Nigeria that are proposing on a mine site to actually sort of move ore in carts from the mine site to the port over an 80-kilometer track. So you've got a steel frame and an underslung pod system. And so it can do shipping containers and everything. This can do our freight. So instead of trucks transporting shipping containers down a road, we put one of these systems in together. Now, when you look at trucks, their transport systems are actually non-linear, as in they're not all roads are the same. There are some routes that take something like 80% of the truck routes, like between, say, a port and a distribution center. So instead of replacing all trucks, we will replace some trucks with this system. Oh, I'll get to it in a moment. Right. So let's say if we have the monorail on top, if we're going to produce electricity consumption per distance per person, put it into an electric vehicle car, right? So we've got that, the green. If we put that person in a bus and it was a hydrogen fuel cell, that's the blue. Or if we put them into a monorail, that's the red. Now, the electricity transport system, the freight system, if we have a truck transporting in terms of kilowatt or kilometer, so we've got a heavy truck, like a big semi-trailer, moving a shipping container, that's the black. The underslung cargo pod system is the yellow to do the same thing. And I'm proposing this. So you have a two-way monorail system on the top and a two-way cargo system on the bottom. So we're not taking out all trucks, we're just taking out some of them. But shipping containers can still be transported between strategically important places. So if we change the layout of our cities, this is to get, how do we transport stuff around a city? So there's a lot of infrastructure to put it in, but once it's in, it can be powered off the grid. We don't need internal combustion engine technology and the fuels to run it as standalone systems. We will still have some trucks and buses because we need the flexibility, but this can take out some. So if we assume, say, 50% of the trucks were replaced by this system, what you end up with is a 21% contraction in the amount of energy needed by the whole system. Yeah. So here's the comparison that I had before, where we've got like the amount of power versus the installed capacity. So the purple transition, if we did all that, it's slightly smaller in installed capacity than what we've got now in terms of fossil fuels. But here's just electricity. Here's electricity and transport. But instead of these massive coal-fired and oil-fired power stations, you've got your thorium molten salt units, which are much smaller in physical size. Right, what would that look like? It was all put together in a balance. So we got the resource-based economy in the center, and around that we've got all the things here. This is all mapped out for Hawaii as a concept. And so we've got, and then if we were to take the circular economy, catch all the waste, put it into a pyrolysis plant. We've got our transport system, put all that together. We've got maritime shippings going out and harvesting plastics from the sea. We're producing hydrogen, ammonia, and methanol for the maritime shipping industry. Yeah, it would look something like that. And along the top in the report, you've also got all the hamlets, 200-person hamlet that can actually make all the food. And I sort of worked out a ratio of how many people would have to be working in that hamlet producing food per 200 people. So which means that people could go off and do something else. Right, conclusions. The task is much bigger than we thought. Transport fleet for split wind and solar are going to struggle to be viable. The Achilles heel is the powered storage requirements. Biofuels should be reserved for aviation fuel only due to land requirements. Conventional biofuels won't work. Consider specially bred species to do this instead. Check it out, though. All conventional approaches had practical bottlenecks in scale-up. It's recommended that the Hawaiian Senate looks at thorium molten salt units very carefully. All right, done. That's it.
Wow. Cool. Well, thank
Are
you.
you alive? The audience is still there. Look at that. Look at that.
Yeah. Ivor, you have a question? Go ahead.
Yeah, I kind of I think it's kind of a landlubber solution, to tell you the truth, because my wife, who's actually from Hawaii, her mother said they had solar-powered hot water tanks on the roof in the 1920s. But also, being on an island right now, I'm thinking, island-to-island transport, you could certainly do by water and skip all this massive amounts of stuff, and and you could also have the wind push them around, in my opinion.
So that's actually in the solution. We do all transport between islands is by ship. They do aviation at the moment, and that's the way their economy is. But it's also by ship. The recommendation is at least some of that goes sail.
Yeah, because I think you could figure out a high-tech version where you use electric motors to get in and out of the harbors.
So all of that's viable. All that technology works, but you've now got to scale it up to be for the full system, and then you've got to get everything into balance.
Oh yeah. Oh yeah.
We killed Charlie. Sorry, Charlie.
Oh, Charlie fell asleep. Hey, Charlie. Yeah, he had. Okay, cool. All right. Is there any other questions or comments about Simon's presentation?
The report's available for anyone who wants it. Andrew, if you could put the link in.
Oh, yes, sure. I don't have the link on me right now.
Hang on, I'll put it in the chat.
Okay, and then I'll put it in the YouTube chat. Okay, good. And so, but I did just want to have a clarifying question about that frequency stuff. So basically, if you overbuild on the solar, then your frequency would be too unstable. Was that what you were saying?
The system's not geared and engineered for at the moment for big changes.
Okay, yeah, and all right, great. And then Graham.
Yes.
Actually, first. Sorry, I was just looking. Julian had his hand up first.
Thank you very much. Is it possible to get the slides? Did you mention?
Yeah, we can do that. I can email them to you, Andrew, and you can post them out to everyone else.
Sure.
Thank you very much.
Okay, now Graham.
Thanks for your presentation, Simon. Josh Floyd and I wrote a book, Energy Storage and Civilization, and we tried to think about how much storage would be required. And we went through the literature, and for the purpose of the book, we came up with a month as sort of a baseline. But it's very difficult, and it's a very fraught area. Now, you've picked 28 days. Have you got any more thoughts on, how much storage is required? Because this is a really critical question that I don't think there really isn't a lot of clarity around.
No, there's not. And it's very opaque, and the industry has been caught with its pants down, and there's a general reluctance to pull its pants up, so to speak. Now, in my published report, I had four calculations. One was 6 hours, which is what conventional thinking believes. One was 48 hours plus 10%. One was 28 days, and one was 12 weeks. The idea was to actually have 4 calculations. So if you subscribe to a different buffer, then so be it. The size of the buffer, the thinking at the moment is everyone has actually done based on the Net Zero America analysis that was done. And what they've done there is the difference between supply and demand between each day. And that difference is only a little. And you only need to store a couple of hours, and you only need to store for about a week to get it all to balance. That's fine. But it doesn't, for example, look at getting through a single night. Like when the sun goes down, solar panels don't work. It also doesn't look at, for example, variations in the weather. It doesn't look at, for example, the difference between winter and summer. At the moment, when we need more energy, we just burn more fossil fuels. So all thinking is still dependent on those fossil fuels. But when you actually try and talk to people in the industry they vehemently deny that. They say, "Oh no! Someone's thought this through. We've basically 40 years of data and everything," and they get quite rude and aggressive about it. And there is no one's actually done a proper study on this, in my opinion. Ewan Mearns came close to doing the best study I've seen, but he's had trouble getting his work published because it actually slaughters several sacred cows, and academia is actually a gatekeeping exercise. It's been very difficult. So no, there's been no clarity.
Yeah, my sense is that the default is, well, we'll just use natural gas or whatever else is available.
That is exactly the default.
Yeah, okay, no worries.
Okay, Charlie, you have to unmute.
Just to respond to that, tell Ewan to write me, and we'll see if we can get it published.
I will do that.
And I'd like to introduce my friend Julian Darley. Julian, turn on your camera for a moment, who just joined us, and he's very, very much on the same wavelength as a lot of people here. And I'm glad to see, I sent him a note too late, but anyway. And finally, the point I would like to make, Simon, is you've met my friend Richard Ha, who tried to grow vegetables in Hawaii and succeeded, but he had a little micro generator run by water on his farm, but nevertheless, he was very dependent upon plastics and all kinds of energy, and food in general in the United States requires about a calorie for every calorie of food delivered. And if anybody interested in that, I've done that in some detail. And just to grow it, and by the time you prepare it and all, it gets all out of whack. So, man, we've just lost the ability to make our own food.
Yeah.
And if you can get the Hawaiians to go back and grow things under rocks and stuff, all the technology that we used to have, I don't know whether you can. What do you do it now?
That's a different problem. Convincing people to change is an entirely different problem. This was a simulation to see, is it even possible? Is it theoretically possible? Is it close to being possible?
Yeah.
And if it was, what direction should we go in? What things definitely won't work? Okay. And
Charlie, how are you going to get us to give up our Kona coffee? That'll start an armed revolt right there.
This is not Kona.
I love Kona.
Well, yeah, I do too, but it's very expensive, so I don't.
I'm just saying, from the mainland, you're going to get an armed revolt if you guys stop growing coffee.
People like, you're going to grow coffee at gunpoint.
Yes.
It's going to be like Banana Republic. All right.
Well, I mean, really, that's what people do. They grow the stuff that grows well where they are. And in fact, think I'm going to give a talk on that to the Canadian Club of Rome coming up in July, middle of July sometime. So I suppose I could give the same talk here if anybody cares.
Sure.
I used to do a whole lot of work on energy cost of agriculture, which is quite terrifying when you do it.
All right. Well, I know we have one more presentation from Dan and Stan. Okay. Are you guys ready for that?
Dan, I loved your report that I read yesterday.
Well, thank you, sir. No, I'm going to
really good, and I'd like to convince you to do some more energy return on investment on all of those massive materials you're talking about.
Right. So can you see my screen?
Yes. It said pressurized electron powered tech.
Okay. So my name is Dan Gowin with Electron Power Technology. I'm part of the Stan and Dan Energy Show. I've got two colleagues I'd like to introduce. That's General Stan Osserman and one of my VPs of sales, George Buskirk, who's also on this call. This here is just simply a spiel for the company, and this basically goes back to this here I'm describing as a decentralized power system, mainly based at the town or county level. That's what our main graphic is for the company. So understand this presentation is simply for educational purposes only. It's just a standard legal spoof that we do just to make sure everybody understands that.
So next slide, Andrii.
Sure. Okay. So, everybody see that? So it's a case it gets picture.
More brace paradox.
Yeah, more brass paradox. So basically, the outage we had in Portugal and Spain has basically brought up this idea about decentralizing the power grid. In this document from oilprice.com, they documented the 22 times that the major grids throughout the planet have actually failed, and unfortunately, one of the common responses to add more complexity to the grid, and hopefully everybody's starting to realize that the complexity is actually your enemy when it's designing power grids, that sometimes you need to break it down to much smaller atomic pieces that are much more survivable. Those that know me know I designed the computer system in the United States that controls the power grid for 26 states and parts of Canada. So I can tell you about trying to keep a grid online and on all the challenges. Understand that before we had wind and solar, our generating capacity in the United States was mainly the old steam turbines and some gas turbines and so forth. But both those devices have what are called spinning reserves, basically a spinning rotor that weighs 20 tons, 300 tons. In the case of gas turbines, usually between 2 and 6 tons. And basically that inertia of that spinning metal basically resists the frequency sag, where you've got more demand than you have generation. The other side of it is when you have too much generation and not enough demand on your power grid, you get too much what we call spinning reserve, and usually the accountants gets upset with this because we're wasting resources rather than supplying energy to customers. So it's good we're actually having this discussion about decentralizing power grids. So what's happened is OPEC has promised 2 million barrels per day. They promised they would start producing or putting back in the market at least 2 million barrels of extra oil production per day. It was a combination, as an agreement between Saudi Arabia and also Russia. Unfortunately, we've got some data from this week. The Russians are still behind their quota. They still haven't put the oil in the market. Not sure if these attacks that they've had here recently have actually contributed to it. But whenever this came out about OPEC Plus was putting all this extra oil in the market, it actually caused a drop in the price of oil a number of weeks ago. One of the problems with this is, according to the IMF, that Saudi Arabia's break-even producing oil is between $90 and $96 per barrel. Understand that's the IMF's estimate of what it costs for Saudi Arabia to produce oil. And if they're selling oil at $60, $62 per barrel, that means that the Saudis are selling it at a loss. Without our banking system that allows the Saudis to basically borrow money to produce oil at a loss, it only allows them to do this. Understand that means that right now the Saudi Arabia has a national deficit of about $17 billion, and by the end of the year, it's probably going to be $97 billion if we keep selling oil at this reduced cost.
Wow.
Okay. Now the question was why did that happen? Why did the Saudis and why did Russia actually agree to that? Well, actually, it goes back to this. So what's happened is the CEO of Diamondback has come out and said that U.S. oil production will drop by 10% by the first week of Q3. Now, a lot of people have theorized that what caused this was because oil dropped down to $60 per barrel. But the reality is all the companies from Diamondback, Chevron, ExxonMobil have cut back on drilling for shale in the United States. Each company has cut their spending. They did that in Q1. Each company cut their spending on drilling for shale by $100 million each for each company. They've also cut back the number of rigs. So the reason has nothing to do with the $60 oil price. They planned on doing this. They did this in Q1. Basically, what the data is telling us is the geology that we've got to the point where we're just exhausting the shale here in the United States. I've got data from, for example, like 2017, the decline rates in the old wells. The decline rates were 330,000 barrels per day was the decline rate. Of course, we had to drill 330,000 worth of new barrels just to keep the production to even Steven, besides adding extra barrels to get the production to grow. By 2021, it had dropped down to 445,000 barrels per day of depletion. Per day of depletion. And right now, the depletion rate is 660,000 barrels per day. And basically, when you do the cost analysis, the amount of what it would cost for you to basically replace 660,000 barrels per day of production of shale oil, plus add growth on top of that, it doesn't justify the cost. Understand that President Donald Trump and what he's done with the trade sanctions and so forth don't help. Wednesday, he activated 50% tariff on steel, so that pretty much guaranteed at least until next year. They're not going to expand drilling of shale. So what we're going to do is we're going to see the production's going to start falling. So you got your Kepler is saying that OPEC's after barrels in the market could be consumed by the shale's rapid decline. They're forecasting it's either going to happen the fourth quarter of this year or the first quarter of next year. We'll start seeing basically a shortage of oil production in the world. And that will cause energy prices to start going up. Understand, more likely, technically, we're probably in a recession right now, looking at our consumption rates of gasoline and diesel. So we're just not consuming as much fuel. That contributes to that low oil price. At the same time, understand, more likely we're going to come out of recession next year, but we're coming right out of next year. We won't have the oil for our global economic to grow away out of it. It's a probability that looks like it's playing out. Okay.
So the demand is going down because people can't afford it.
Right. Well, what it is, the economy right now is contracting worldwide. For example, Chevron announced they basically laid off 800 workers there in Permian for drilling shale, and that's just in the oil and gas industry. If you look at all the other business, for example, I think IBM laid off most of their HR staff due to AI technology. So there's a lot of massive layoffs going right now. So, I mean, you look at the consumption rates of our diesel and gasoline, the consumption rates are falling, and that's due to basically people, starting to lose their jobs. People tighten up their spending. They're not driving as much and so forth. They're not flying as much to Hawaii to go on vacation, etc. What's contributing to this is the U.S. fall in credit rating from AAA to AA is affecting smaller operators' fundraising. Why invest in private enterprises when a greater yield can be had with U.S. government bonds? So a lot of your small drillers, for example, like Phoenix Energy, they're up in North Dakota and the Niobrara, down there in Colorado, they're having a hard time basically getting investors. They're saying these have to be qualified investors to invest in. They were talking about not stock, not private stock, but actually bonds with these companies that pay 9 to 13% return. So understand right now the big majors are looking at gobbling up a bunch of these guys, but at the same time, the big majors, even though they're going to probably add more acreage onto what they've got, obviously they're gonna keep the wheat and throw away the shaft. So if you've got small producers out there that have marginal production, that's probably going to get thrown into the shaft pile. So the big majors are only going to keep the high quality stuff, but at the same time, they're cutting back their investments in producing shale. If you want to know what they're looking at the solution to low prices is low prices. They're looking at a rebound in oil prices back above $90 a barrel, probably within a year, 2 years from now.
Oh, okay.
Yep.
Interesting.
So the drillers doubled down on location. Okay, so the U.S. has already seen the closure of the Lyondale, Basel, Houston refinery there in Houston on Refiners Row. 2 California refineries, that's Wilmington and Benicia, have shut down. That's the Phillips 66 there in L.A. Those will shut down probably sometime this fall. Gavin Newsom is begging both the companies, I think it's Valero and Chevron, not to shut the refineries down. But the problem is he can't counteract the economics of why they're shutting it down. And basically he says the only way to counteract lower margins and weak demand growth seems to be capacity consolidation. What that means is probably starting the end of this year, going to next year, you're going to see a global diesel shortage. One of the things Stan and I talked about is there's a refinery there in Hawaii. Maybe in the next couple of years, you're looking at it'll become much more economical to ship fuel to Hawaii rather than refine crude oil into diesel and gasoline there in Hawaii. And it has to do with demand destruction dynamics.
Mm-hmm. And a lot of what kills these refineries is just the upkeep and maintenance. As they get older, a lot of these are getting older, and the upkeep, the cost of running them goes higher and higher, and those companies just want to dump them.
Yep. So you got to, so this basically hit the Wall Street Journal. Understand last year, the narrative was basically the United States had enough oil that they'd be producing crude oil all the way out to like 2050. Then in January, the narrative changed to, well, maybe sometime in 2027, peak oil and peak shale gas will occur in 2027. Now the Wall Street Journal is coming to the truth that no, that oil production in the United States has peaked, and that, understand that was on May 17th. Now in the article, they're downplaying the decline rates, like, oh, we'll have this slow 1 or 2 or 3% decline rate out for the next 50 years. But the data on the shale fields are pretty brutal. The decline rates are really steep. I mean, if you go back to Diamondback, they're saying that our production will drop by 10% by the first week in July. That's here in a couple of weeks. And if you look at that we were at 13.8 million barrels per day right now. That means that you're talking about 1.3 million barrels a day production will drop. So it'll drop down into the 12s. And what the companies are saying is the decline rate will accelerate. Just understand that's the wells that they've got under their management that they're seeing the decline rates. And so basically as time goes on, that 2 million barrel surplus will be gone by July. And then by this fall, the whole 2 million barrel surplus from Saudi and Russia will be completely gone. And you'll be seeing the first parts of the crisis. Now, understand that not everybody in the area is agreement upon this. Of course, you got Exxon Mobil and Chevron and Diamondback and Lepers and the rest of those guys that it's their business. They know their fields, right? What they're saying. And then you've got guys like Anis Haji, who's an expert in this area, and he's basically holding his powder, basically, so to speak. He's saying hold off until we actually see the decline rates this fall. So I'm just trying to tell you the most conservative analysts in the field are saying hold off until this fall till we see what the decline rate. So that's Anis Haji, and the other one is Christine Geraro, who's a petroleum engineer. She's been talking about this also, and she's also the one that's brought up the issue with the frack water. That one of the limitations of producing oil, the Permian is trying to get rid of frack water. That was the real limitation, not really gas. So. So this goes back to oil depletion rates will accelerate. So if you understand ExxonMobil's global energy outlook, the executive summary and the executive report that they did last August, This is all playing out according to ExxonMobil's global energy outlook. The biggest issue here is that white area there, and that's basically, we haven't discovered any new major oil field in the last 25 years. For example, if you look at the oil fields we've found the last 10 years, the majors, people like Guyana, what everybody misses about Guyana is you're talking about 11, the reserves are 11 billion barrels of BOE. Notice the term BOE, barrels of oil equivalent. If you look at the gas oil ratio, I mean, just to be generous, let's say 50%. So that's not 11 billion barrels of oil. That's actually 5.5 billion barrels of oil.
Oh,
and
wow.
in the United States, we consume 20 million barrels of oil per day. I can take just some simple math, divide 20 million barrels a day into 5.5 billion and tell you that, yeah, the United States could eat Guyana in less than a year. So so the problem is we just aren't finding the oil. Yeah, we're finding a lot of gas. So you hear a lot of the guys talking about gas. There's a great future of gas because that's really what they're finding is gas and gas liquids. So anybody doing these oil, you need to be very careful because these guys have switched. Back in 2018, they switched from oil to switch to BOE, barrels of oil equivalent. And you dig in the numbers, you'll find out a lot of your oil isn't oil, it's gas. That they're basically saying this gas is a BTU equivalent to oil. Gas is not oil. You could turn gas into oil, but it's a pretty tough road to row up to try to convert, natural gas into oil.
And that's supported by Roger's briefing earlier.
Yeah,
if you're
yes,
paying
it is.
attention.
Yep.
And also point out, Guyana and Venezuela are disputing this territory of this new oil field. So that means potentially there's a conflict, a physical military conflict boiling underneath the surface of just this one oil reserve.
Yeah. The part there where it says investment in existing fields, that light green you see right there, that's like that continental CO2 system I've been telling you guys about. So basically, if we don't invest the $5 trillion in the continental CO2 system to basically do enhanced oil recovery on our existing fields to maintain production. So that means, I mean, if you look on the positive side, by 2030, the production will drop from 104 million barrels a day down to 75 million barrels a day. If we don't do the investment in the continental CO2 system, it could drop all the way down to 35 million barrels a day. So you're talking about world consumption. And if you also notice on the next chart outside, they're also talking about gas, because remember, gas is associated with oil, and they're talking about the same steep depletion rates for the gas field. So what ExxonMobil is trying to tell us all, we're looking at the gun barrel of a major energy crisis, and right now it's everything is falling in line with what ExxonMobil is projecting for the world.
What Dan usually says is if they're talking about building a gas transportation, LNG plant for moving and pipelining LNG, it's because their oil resources are declining.
Yeah, I got the old saying that when it comes to oil fields, the last thing that passes through the wellhead is natural gas. Watch what they do. Don't listen to what they say.
Mm-hmm.
So, next one here. So this here is a picture. It's about 300 yards away from the Laherrere binary geothermal power plant. This well was drilled in 1973. It's 10,383 meters deep. The temperature of the water that's coming out of the ground is about 320 degrees Celsius. The reason why this well was drilled is because in the late 60s and early 70s, there was a huge question. Well, what it was is that the sedimentary basins in North America, about 7,000 meters deep, they weren't actually sure what was underneath the basin. So that's why this well was drilled. And what they found at 10,383 meters deep is that the rock turns into a basalt that's highly fractured and is full of water and hydrogen. So the point being is this well here was the reason why they built the Laherrere binary geothermal power plant there in Idaho and brought it online in 1980. So that's the presentation.
All right. Okay. Are there questions from the panel? I know I have a question here, or more of a statement here. Said Raymond Simmons says true parallel paths avoid brace paradox. I don't know if that's relevant at all, or do you understand what they're saying?
Say that again, please. Say that again, please.
They're saying true parallel paths avoid brace paradox.
I don't know.
I would disagree with that based on what Dan and I have been talking about. Is the whole basis of Brace paradox is it's counterintuitive, because just because you have two parallel paths, the human community is going to start picking one or the other, and it'll eventually overcrowd one of them, even though in theory it should relieve the strain and the paths. But because people make choices for weird reasons, we've always done it this way, or it's closer for me to go this way, you can still overload one path even when you build a parallel path. So that's the basis of Brace paradox. In other words, I call the idea that you have unintended consequences when you do something you think is going to be good. A lot of times you have unintended consequences that drive people to go and make it worse, and that's the whole point behind Brace paradox.
One of the parts about Brace paradox that everybody doesn't seem to grasp hold of, it really is a function of complexity. Right. So, for example, if you look out there in Wikipedia and Brace's paradox, you load down through there, you'll see this little snippet of code written in Pascal. So that's a piece of code that I wrote. And the basic function is that basically as your complexity increases, right, the effects of the Brace paradox and basically the effect of a catastrophic failure increase exponentially based on the complexity. And if you want to understand the basic idea there, it goes back to Murphy's Law. Anything that can go wrong will go wrong. The more complex the system is, the more chance it has of going wrong, and you get these cascading failures. I'm also what most people do, especially people that run power grid. Their first response is, "I'm going to add more stuff to my system. Keep adding more stuff, and that'll fix what broke." And so they're always fighting that last war, not realizing that no, you're making it worse by adding more complexity to the system. The counterintuitive thing to do is go the opposite direction. Break it down into smaller atomic pieces. For example, the internet, that's how the internet is built. So if a piece is lost, it routes everything around the part that's lost. For example, the military, we think of things in the same way. We use small atomic units that if we lose one, we can route around it, and it's not a critical piece that's going to affect the overall effect of what we're trying to accomplish.
Okay. Ivor, you have a question?
Yes. Well, it seems like what you're saying, Dan and Stan, is holy crap. We are like on the edge of a major problem, and like the fact that oil will be down by 10%. Q3. I mean, it's like
that's what the CEO of Diamondback is saying. We're talking about a major corporation. Yeah. I mean, Diamondback, Chevron, and Exxon, all three of them cut their spending in Shell by $100 million each. All three of them. They did it in Q1.
Do you think that we're going to make it up with, I don't know,
NGLs?
Extra oil, or what are we going to?
Well, the first presentation I did a couple months ago, I talked about some of the offshore stuff we have, these two oil fields, and basically production of those have been delayed because oil prices are too low. To do offshore oil, they need $90 or higher just to pay for those drill rigs. And if you look at those oil fields, yes, there's oil up there, but it's $20 a well. You got to drill a minimum 9 wells. That's $225 million. To a quarter $1 million just to drill one well. That the company up there is having that county on resource having problems getting funding. They've got 2 new oil fields they want to bring online, but they need to have $750 million just to get started to start bringing that oil line. So it goes back to what's the cost of that oil, and then it goes back to like Andrii, what are you willing to pay for gasoline and diesel? That's a big question. What does Andrii say? I'm going to walk over to the strip mall. I'm not going to drive my car. And that's where you get this. There's a ceiling here, and here's the bottom, and the bottom's coming up to reach the ceiling. So there's oil out there, a lot of it. But the question is, what will it cost to bring it, to your service station?
And just to make things interesting, Dan, what is the break even for Russia, the Middle East, OPEC, and the United States on oil? Or you have to, it's a minimum that you got to do to break even.
Well, Russia these days is about $35 a barrel, but understand their depletion rates are like 6%. So maybe that's true for maybe the next 10 years. In the Middle East, the Saudi Arabia, you're talking $90, $96 according to the IMF. The low-cost producer there in the Middle East is actually Kuwait, but remember, they're only producing maybe 100 million to 200 million barrels a day. So you could easily swamp their production if you try to buy up all the oil. And I think they're about $35 to $40 a barrel. But it doesn't change the fundamental fact that for the last 10 or 15 years, oil production in the world was being filled by the shale oil, by the Permian, by what we're doing here in the United States. And now that's gone in a terminal decline. And so then it goes into, okay, what's the new one? And also understand, I showed you that chart from ExxonMobil, it's not like these guys haven't been looking for oil. The oil companies have been spending between $40 and $50 billion a year for the last 25 years looking for those new oil fields, and they just haven't found much.
What's the break even for the U.S.?
Well, for the shell, 75.
Okay.
Wow. I know Charlie has a question. Charlie, you have to unmute. You have to unmute, Charlie. You have to click the button.
Are you still bullish on deep geothermal?
Yes.
Yes. Okay.
Yeah, because I think we're going to get a situation where you're probably 80% of the United States you could do geothermal and do it inexpensively. Also, come to the idea that most communities will probably accept that versus nuclear power. I think that that other part of it, you'll end up doing
short piece, and I'll get it.
Okay.
So, I'll think about putting something together, Charlie, and I'll send it to you. I don't know how long it'll be, but yeah.
Yeah. Oh, on that topic, I was talking to UC, who owns the deepest official geothermal project in Finland, and then also was getting that Joseph Moore, who's doing the Utah Forge geothermal project. Yeah. So I don't know if you or Simon had any comments on that. I know I CC'd you guys in the emails. I don't know if any of them got back to you or anything.
When I looked at some of the data, what I saw were horizontal wells. The oil and gas business has moved into this directional drilling stuff for like the last 20, 25 years. So that's one of the things that one of my comments. The other one was the wells were shallow. Almost all the drillers I know these days, they use these drill rigs. They're directional drill rigs. They're called 7-kilometer wells. Are actually drilled deep, 7 kilometers or deeper. For example, the laterals, like the pipe I'm putting in the ground over in Ohio, the shell's 20,000 feet down. The laterals are 25,000 feet. There's 45,000 feet of casing we're putting in the ground. That's 13.7 kilometers worth of steel casing. So one of my complaints about some of these geothermal companies, I don't know what's happened. They're like stuck in the past or something. With the oil and gas business, they seem to have newer equipment and better equipment. Just looking at what they're producing, even for example, that Deepwater Horizon, that accident we had in the Gulf, back in 2010, from the blow-up preventer that was sitting in the bottom of the ocean to the bottom of that well was 36,000 feet. So I'm not sure why there's this disconnect. You would think that the oil and gas drillers and the geothermal guys would be the same group, but they're not. So, Simon,
Andrii, before we get too close to the end of this, I'd like to thank Simon for his work on that Hawaii report. I had a little piece to play in it, but Simon, we really appreciate it. I think that the world can take a look at that, and it opens their eyes to the realities of what we're facing and the challenges we're facing. And I think what it really tells me is that our leadership, our governors, our mayors, our public leaders, they have a huge issue in front of them. Dan's just outlined one of the huge issues, and that's energy costs and oil. And you're sitting there trying to say, well, here's how we can fix it. And there's a lot of costs involved in that, and nobody's doing anything. I mean, they're basically kicking the can down the road, and we're all going to pay the price in the end. And it's going to be a big price. So thank you for doing that work, and we really appreciate it.
You're very welcome. So how's it been received in Hawaii? Like, how's it? You're in Hawaii, right?
Right.
Yeah. How's it been received locally?
Well, Peter's trying to set something up with the legislature where we actually do a formal presentation and hopefully invite you over there to do that. So far, it's just being digested. And quite frankly, it's a complex, it's a long document. It's going to take some folks a while to get through it. But I kind of think that a presentation like you did today might be a good way to really expose more people to it who don't have the time or the intellect to go digging through all that work that you put out.
We did a recording. Peter and I did a recording of the review panel, and he's edited. I don't know what he's done with it. So one of the comments that I've heard other people, not me, I didn't say this, is when they're trying to convince people to do it, they say comments like, guillotines don't need energy to run.
Yeah.
That wasn't me.
Yeah.
Well, if I may jump in here, gentlemen, my name is George Buskirk. I'm, for lack of a better title, Dan Squire, and in the process. Thanks to both Roger and Simon.
Go ahead, George. You cut out.
Yeah. Back there. Mm-hmm. Okay. I wanted to say thanks to Roger and Simon. Very informative. On the agricultural side, I had recommended this to Dan the other evening. Don't let the political leanings Harrelson, I think they had Woody narrate it so that, people think if Woody can understand it, anybody can understand it. But they do a very good piece, has a lot of carbon recapture, but it goes specifically into the way to transfer the farms back to regenerative stats. I live in the heartland here, so I've watched 2 fields out my window, one no-till, one till, both kicking up tremendous amounts of dust, but I won't diatribe too much into those. But I think the agricultural side of it, what I've already seen Hawaii do, is pretty impressive. I spent some time on Molokai. I did not have the political pushback. I saw a couple elders and things and mentioned.
You're breaking up, George.
Yeah.
Yeah. George, could you put the link to that documentary by Woody Harrelson? Could you put it in the chat so that way everybody can get it?
Yeah, I will.
Okay.
I will do that. And I did not have the political pushback in Molokai from Native peoples.
You might need to turn off your video, George, when you're talking, because it's not able to do both.
Too much.
Okay.
How's that? Any better?
That's better.
Okay. The political side of it, I have had more Native peoples express they believe that is a gift from pay, and I've experienced pushback on.
You're still breaking up, George.
Sorry. Sorry, George. Yeah, I'll have to figure something out with your internet for next time.
You're okay. I will pause. Thank you.
Okay, thanks. I had a question for Simon. If you had any feedback on the deep geothermal, because I know that's in Finland, and I don't know if they talked to you at all. Mm-hmm.
I went to talk to the GTK professors on that, and what they basically said, look, these are new ideas that are coming in. The challenges geothermal faces, there's a number of practical challenges that in terms of the amount of energy at depth and getting it up to the surface it's still in a useful form. So once you drill the hole, you've then got a whole series of practical problems to get through. There's a number of engineering hurdles to overcome. What they basically said was, well, we still see some bottlenecks. Will these ideas help? Let's see. That was the response. So in terms of, it wasn't a flat out, no, we don't believe it'll work. But they said, look, this might resolve some of the problems if it does work. And if it does work, then we've got other problems to get over. So now I'm not a geothermal expert. Like I've got an analyst's view of it. These guys work with geothermal. I take the point though that they're using old technology. So And my answer is, let's see. Someone's working on this, as I understand it. So let's see what they can do. And if they get the revolution, then we get the revolution.
Right. Yeah. My idea was with the aerogel sleeves, and I was hoping the Finns would work on that. But I don't know if we can get them on the show at all. Any of those professors?
Good luck with that.
Good luck with that. Okay. They're not big on public appearances.
Andrii, what we need to do is the oil and gas industry has lots of really great data, and they've got the technical talent to do this. And there's already some expertise in that community. One of the bigger players in this is actually Baker Hughes, and that's who needs to play in this. But the people that applied a lot of money to actually working on this, and that's what needs to happen.
So. Do we know some geothermal experts we can get on the show?
I don't know, Stan. We've had some geothermal experts and some of the other stuff you and I've done there in Hawaii.
Yeah. So we're doing a production. Renewable Hawaii is doing a forum on geothermal coming up on the 29th of this month. So you could go and look for Renew and Rebuild Hawaii, their website, and you could listen in on that. That company is called Sage out of Texas. And they do deep drilling, directional drilling. There's a Canadian company called Eavor, EAVOR, and that's a closed loop system. And what Dan and I've talked about with geothermals, you really have to consider using binary systems because it allows you to use the lower heat grade from your wells, and it also keeps your turbines from requiring so much maintenance. So again, just some good things that you could look into.
We've got a lot of stuff where the Department of Defense has pioneered a lot of this stuff, and for whatever reason, we're having a hard time trying to get the civilian sector basically picking up a lot of this. And unfortunately, with the DoD and the DOE, we're basically just running on grant money. When we brought Raft River online back in 1980, you would think that the public utility business would be jumping for joy for it. They haven't. They just sort of let their languor. And understand that was back in the 70s. We were transitioning from oil, and what they chose instead of doing geothermal, they chose, we're going to go burn coal. And at that time, they said, well, the geothermal's too new. Well, here we are 45 years later, and they still are reluctant for whatever reason. So.
I think Simon also wanted to say something, and then after that, we'll go to closing comments. Simon, did you have a remark on this, or
no? I was just that. No. It's just to say, like, I talked to the guys, the geothermal world, whether they've got the best drilling technology, that's a different question. They're of the opinion that there are some hurdles with regard to the energy contained at depths and getting it up to the surface to be useful. The drilling question, I used to be in contact with a group that was looking at electrodynamic fragmentation for drilling. So the drill could actually go down. I actually saw this, and it works. And what it meant, though, was that they could break the rock with electricity in an oil environment. If that works, what that means is the drill bit never touches the rock, which means it doesn't jam. And that's the problem with these deep drills. So there is technology out there trying to do this, and one day someone will get a breakthrough. So if we can drill the hole deeply, quickly, fast, cheaply, that's one set of problems. The guys I sort of talk to, and it could be that they're just conventional thinking. They haven't come across new ideas yet. They haven't thought about the implications of new technology. But they were trying to tell me that we've got a series of natural problems to overcome as well as the drilling. Whether that's really the case or not, I don't know. So, Dan, have at it. More strength to your arm. Give it a go. See what happens. Boom.
Well, I can. In the case of the Raft River, that was a closed loop, and like I said, the hydraulically fractured rock, 11 kilometers underneath the surface. But the idea was both the wells were pressurized. In the case of the water being injected in the well, cold water is dense and very heavy, and it likes to flow down, push itself back down into the ground. Versus on the other side with the production well, the water coming up, it's hot, it's expanding. And for example, there at Raft River, they only use a 5 horsepower motor to actually move the water through the system. So, and if you want to know what they were powering that little 5-horse motor with, was a bunch of solar panels, just to keep it circulating through the heat exchanger. It's a type of power plant where you can actually do dispatching because you're circulating the heat, through your heat pump system continuously, using really low energy systems. And then, like I said, you could ramp your power plant, your turbine, from your 5 megawatts up to the 140 megawatts and back, and because you're tapped into an infinite power source. So,
I recommend students in a hamster wheel.
Yeah. So that's how they got the energy out. But the key was keeping it pressurized, keeping the system pressurized. It has a lot in common with like pressurized water reactors. Because remember, there was submarine guys that came up with this.
Ivor, and then we'll go to closing comments.
I've heard that there's a big problem with money. Basically, nobody trusts any kind of, they're not trusting bonds anymore. They're not trusting the U.S. dollar.
Whenever the United States lost its credit rating, remember there's three different credit rating agencies. There's Fitch, there's S&P, and there's Moody's. And Fitch and S&P already downgraded us, years ago. Moody's was sort of the last straw, and they downgraded us from AAA down to AA. That had a ripple effect through insurance companies, pensions, all over around the world. A lot of these institutional sources of capital have these bylaws that say thou shalt only invest in AAA rated stuff. So all of a sudden America became less. That had a ripple effect to all the drillers, and also it's affecting the geothermal people trying to get me also. So yes, the financing's even gotten even more tight. Yep.
Oh no. Okay, thank you.
All right. So, and then I wanted to add a clarifying point here that according to ChatGPT, anyways, Raft River is 3 miles or 15,000 feet deep.
Sorry. Nope.
Okay. All right. So anyhow, closing comments.
I bet ChatGPT doesn't know anything about that picture I just showed you with the steam shooting up out of it either.
Well, there's an Intel G test bore at 10,000 feet, which is 3 kilometers. And yeah,
after Roger's briefing, I'm not sure I trust ChatGPT.
Yeah, I'm fairly certain. For example, like all the wells out at the INL, none of that's on your ChatGPT. Anything out there at Raft River, that was part of the Department of Energy. That was that's a military federal reservation. I'm sorry, it's just.
Yeah, it's possible there's some classified stuff that's not there.
Yeah.
All right. Okay. So
I'm gonna try just one question for Dan. The Ludington power plant up in Michigan that gravity feeds, is that efficient to use the offset solar power?
I mean, right. Originally, when there's a reservoir that's up there north of New Holland. I mean, originally what that was for was backing up Cook down there in the south side of that 2 gigawatt nuclear power plant there on the south side of the lake. So basically, whenever originally was in the nighttime when we had max power of the nuke, we would pump water up behind the lake, and then in the daytime when Chicago, all the lights and stuff fired up, we would basically drain water out of the lake to generate the extra power to pick up the peak, there in Chicago. Since we've shut down Cook, now we're taking all the excess wind power and using that to pump water back behind the reservoir. But the limitation on that is the reservoir. And not only that, but you can't do that every place.
Right.
The geography kind of limits you. Yeah.
all right. So, okay. Any closing remarks before I close the show? Okay, Charlie, or are you saying goodbye? All right. So otherwise, next time, hopefully we'll get some geothermal experts on. Otherwise, we'll have a continuation. I think Simon had some things on China, which could be interesting to hear.
I can show the China snapshot, and that will you'll either laugh your ass off or you'll be scared shitless. One of the two. All
right, cool. Well, join us next time for that. And so, as I found you, leave you in the love and in the light of the infinite creator within you and all around you. Oh, wait, Dan, you have something to say?
No, I'm fine. Go ahead.
Oh, okay. All right. Go forth, therefore, rejoicing in the power and the peace of the infinite creator within you and all around you. My friends, Adonai. All right. I ended the stream.